Okay, so now we're going to talk about another variant of induction called complete induction. This one's not as simple as induction from the starting point, but I think it's relatively straightforward. Okay, so what's happening with complete induction? Say we want to prove that we have some predicate P on the natural numbers, and we want to prove that P of 5 is true in particular. We're really interested in 5. So what's happening with induction, with regular old induction, is that we say, okay, so we know that P of 0 is true, and we know if P of 0 is true, then the next one is true, so P of 1 is true. And if we know that P of 1 is true, then we know that the next one is true, so P of 2 is true. And we know the next one is true, so P of 3 is true, and the next one is true, so P of 4 is true, and the next one is true, so P of 5 is true. So that's what's happening with induction. But sometimes the statement is such that in order to prove P of 5, it doesn't suffice to just know that P of 4 is true, but we also have to know that P of 3 is true sometimes, and that P of 2 is true, and that P of 1 is true, and that P of 0 is true. And those facts, that those guys are true before we prove P of 5, should be accessible to us. We should be able to use those facts. And that's what's captured with complete induction. Okay, so let's look at the principle of complete induction. So suppose we want to prove that P of n holds, some predicate holds for all natural numbers n and n. So the goal here is not different than with regular induction. The goal is the same, that we want to prove P of n for all n. We can do this if we know two things. So if we know, first of all, that P of 0 holds, so that's the same as with regular induction, and we know the following, which is a bit, seemingly seems to be a bit stronger than with regular induction, which is that for any natural number n, if P of m holds not just for m equals n, but really for all the guys up to and including n, then P of n plus 1 holds. So if we can say that if P of all the guys before and including n hold, then P of n plus 1 holds, if we know that, and we also know that P of 0 holds, if we know these two things, then we can conclude that P of n holds for all n and n. So this principle of induction just gives us a, you could say, a stronger hypothesis. It gives us some stronger tools to prove that P of n holds for all n and n than just what regular induction gives us. Okay, and I also want to point out, which we'll see in the following example, that we can also combine this variant of induction with the last one that we talked about from a starting point, and we can start complete induction, not at 0 as I've written it here, but at any number. So we can start complete induction at 0. Oops, should finish the sentence. We can start induction, complete induction at 0, or we can start it at any other point. So let's look at an example that actually combines these two variants of induction. Okay, so let's let our predicate, P of n, be the statement that n is a product of primes, or more explicitly, so that n being a product of primes maybe isn't so clear what exactly that means. So we can say more explicitly that n equals p1 times p2 times p3 dot 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 times pm for some integer m. So there has to be at least one of these p's, but there could be 1, there could be 2, there could be 3, and prime numbers p1 through pm. Okay, so that's what I mean when I say that n is a product of primes. So it doesn't have to be a product of exactly 2 primes, which is maybe one understanding you could have of the first sentence, but it could be a product of just 1 prime and could just be equal to 1 prime by itself, or it could be equal to the product of 2 or 10 primes. Okay, so we want to prove that P of n is true, certainly not true for 0. P of 0 is not true. P of 1 is not true. But P of 2 is true. P of 3 is true. So we want to prove this for all n greater than or equal to 2. So we want to prove P of n for all n greater than or equal to 2. So we're not going to start at 0 for this induction. We're going to start at 2. And this statement is part of the fundamental theorem of arithmetic. Fundamental theorem of arithmetic is a bit stronger. It says that the way you can write a number as a product of primes is unique, which we're not going to talk about in this proof. But it is part of an old and famous theorem. Okay, so let's look at what the proof should be. So let's say here we proceed by, and I'm going to say complete induction. So complete induction is different enough, I think, from regular induction that we should use the word complete when we write our sentence. Just tell the reader what's going on so they're comfortable and they're not confused about what we're doing. Okay, so for the base case, we've just discussed that our base case should be p of 2, not p of 0, but p of 2. That should be the first number for which p is true. So we will prove that 2 is a product of primes. But again, we're just going to use our knowledge from, I don't know, middle school or something, that 2 actually is prime. Let's say, but 2 is itself prime. So it is a product of primes. It is and sometimes a trivial product of primes. So it is a product of primes. In particular, it's the product of just the prime 2 by itself. So we just have, like in our list here, we have that 2 is equal to not a whole bunch, not the product of a whole bunch of primes, but the product of just one prime, which is 2 itself. Okay, so 2 is trivially the product of itself, which is prime. Okay, so for the inductive step, we're going to use complete induction, and it'll be clear why once we get into it. So for the inductive step, we're going to assume that P of M holds for all M less than or equal to N. So that's what our inductive step says. But we are not starting at 0, we're starting at 2. So we also want to say that M is greater than or equal to 2, because certainly P of 0 is not true. So we have these bounds on both sides since we're combining complete induction and induction at a starting point. Okay, so we're going to assume that P of N holds for all of these M's. Now we want to show, actually let me write what P of M is in words. So let's write that M is a product of primes for all M between 2 and N. We want to show that this is true for N plus 1. So we want to show, we want to show that N plus 1 is a product of primes. Okay, so that's what we want to show. And now we're going to use a little ingredient from the heavens, which is the law of excluded middle. So the law of excluded middle, let me say up here in the corner, that the law of excluded middle, which is often abbreviated like this, says that A or not A is true for any proposition A. Okay, so we talked about this briefly, but we didn't focus so much on stuff like this because it's equivalent to having proof by contradiction, which we didn't focus on in the logic part of this course, but in this proof we will use the law of excluded middle, which hopefully also seems obvious. So we know from the law of excluded middle that either n plus 1 is prime or it isn't prime. So this is by the law of excluded middle. And now we can use this to do a proof by cases, one case where n plus 1 is prime and one case where n plus 1 isn't prime. Okay, so let's say if n plus 1 is prime, so this is the first case, then it is a product of primes. It's just a product of itself, just like 2. N plus 1 equals the product of the 1 prime, n plus 1. Okay, so if n plus 1 is prime, then there's really nothing to do. It is kind of trivially a product of primes. Okay, so now let's suppose that if m plus 1 is not prime, then by definition, so we'll talk a bit about prime numbers, I think, later in the course. But if you don't remember, being prime means that, or being not prime, let's say, it means that you're the product of two guys that are not one or yourself. So by definition, there are natural numbers, let's say a and b, such that so their a and b cannot be 1 or n plus 1. So they can range from 2 to n. And the whole point is that their product is n plus 1. So if n plus 1 is not prime, that means exactly that there are two natural numbers whose product is n plus 1 and which are not 1 or n plus 1, because of course, then nothing would be prime if that were allowed. Okay, so we have this, and now we have something where what we have here is getting kind of close. Let me give this a different color. So what we have here is getting kind of close to what we want. Let me bring down our statement. It's getting close to what we want, but we don't know that a and b are prime. But we do know from our inductive hypothesis that a, since a is between 2 and n, we can use our inductive hypothesis that a can be written as a product of primes. And the same is true for b, of course, because a and b are the same as far as we know. They might be the same. They have the same properties. So we can say by the inductive hypothesis, A is equal to some product of primes. So let's say it's equal to that product, and B is equal to a product like this. And let's just point out that these guys are primes. Okay, so we know by the inductive hypothesis that A is a product of primes and B is a product of primes. Thus, n plus 1 equals AB is, of course, the product of all of these primes. Okay, so now we see that n plus 1 is itself a product of primes. And let's just think about what happened. So we couldn't use, let me choose a different color. We couldn't use our regular principle of induction. We had to use complete induction because we had these two guys, A and B. And of course, we don't know if they're equal to n. We don't know if they're just one less than the guy that we're interested in, n plus 1. They could be anything between 2 and n. So we need to use this principle of complete induction so that we can say something about them, because they might not be the guys right before n plus 1. They might be a little bit further back. But with the principle of complete induction, then we can also say something about these guys. Okay, so we can finish up our proof and say, therefore, by the principle of complete induction, we find what we were hoping to, which is that n is a product of primes for every n greater than or equal to 2 in the natural numbers. Okay, so that's it for this video. In the next video, we'll talk about alternate forms of the principle of induction.